All right, welcome to this video. In this video, we're discussing in-class activity 11A, Introduction to Power Functions. In preview assignment 11A, you investigated the drag force that a cyclist experiences while riding a bicycle. The drag force D is a function of the velocity of the cyclist and is expressed by the power function d of v equals 0.383 v squared. 1. What are some reasonable values for the cyclist or the speed of a cyclist in miles per hour? Okay, so if we think about normal city riding environments, average speeds could be maybe around 11 miles per hour to 12 miles per hour. Often we're going to be asked to work in meters per second as well. So if we wanted to, we could write 11 miles per hour as about 4.9 meters per second, and 12 would be about 5.4 meters per second. Objectives for the activity. You will understand the definition of a power function. You will be able to evaluate and graph power functions, compare and contrast different power functions. 2, based on the range of reasonable values for the speed of a cyclist in meters per second, fill in the table shown and graph the drag force function D. Be sure to label the tick marks on the axes round to the nearest tenth. So if we start here, I'm going to go ahead and copy this function D of V equals 0.383 V squared down here at the top. And the chart of the table, it starts with 0 and 0. So if we plug 0 in, obviously we're going to get 0 out. But let's just go ahead and try some values. If I put a 2 in here, all we're doing is replacing the V with a 2. So we get 0.383, and then we'll have 2 squared. Following the order of operations, we get 0.383, 2 squared, and I'll make that a parenthesis, is 4. And then if I go to the calculator, I have a calculator app here. It looks like a TI-83 roughly. And I'm going to open this up, and I'm simply going to hit 0.383. And then we're going to multiply this times the 4. And I get 1.532. So let me go back here and write in 1.5. It's a 0.532. The directions tell us to round to the nearest tenth, so I'm simply going to put a 1.5 into my table in that drag or D column for newtons, 1.5 newtons. Let's try this again. If I were to take D of, I'm going to go up to 4 here. That's 0.383, and then we'll go 4 squared, and 0.383 times 4 squared is 16. I'll do the same thing. Let's go back to the calculator, and we'll go 0.383 times 16. Whoops. Let's clear that. 0.383 times 16, and we end up with 6.128. 6.128. Again, rounding to the nearest tenth, that would be 6.1, and I'm going to fill in 6.1 in our chart. Now the rest of the numbers in this chart and the rest of the rows would be filled out the same way. If we just continue, we're going up by 2s. What do we do with 2, 4, 6? We could do 8 and 10. And if we plug in D of 6, this would end up by the same process, about 13.8. We do D of 8. This is going to give us about 24.5. That's after we round to the 10th place. And finally, I'll just put this over here. We do D of 10. We are ending up at 38.3. There we go. Now we have to graph these. We've been asked to graph these. I'm just going to move this up so we can see the graph here at the bottom of the screen. What I'm going to do is I'm going to look at the velocity column, the V column, and I'm going to put an arrow under it right here. So I'm looking at that first, and I'm going to go along the horizontal axis, starting at 0, and then we're going to count up to the top number there, 10. So it's going to be 1, 2. 1 second here. Let me make some room. I'll start again, and we are going to make some room. We go 0, 10 is going to be at the top. And let's see. We do 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And then if I look at the next column, and I just put the arrow under the drag column in newtons there, it starts at 0. On the vertical axis, it goes up to, the numbers go up to 38.3. But let's just make that like an even number, like a 40. And then we'll count up by, break that in half, 20. So let's go up by 5s, 10, 15, 20, 25, 30, 35. There we go. And I'm just going to plot these points. We start at 0, 0. So I'll put in the corner there at the origin, I put a 0, point for 0, 0. And looking at the next row of our chart, it says 2 and then 1.5. So I locate the 2 on the horizontal axis, and we're right there. And I go up to 1.5. And that's going to be pretty close to the horizontal axis. So it's just barely above the axis there. If I go up to 4, the next number, where I just drew the arrow under that 4, we go up to 6.1. So roughly there. And then 6, 13.8. 8, 25, 24.5. So just under the 25. And then finally 10, and then 38. So it's going to take us up pretty close to the top. And then what we want to do is connect these dots with a smooth curve. There we go. Let's move on to the next question. Part number 3. It says if a cyclist increases their speed by 0.1 meters per second, by how much does the drag force change? Well, the answer is it depends on how fast the cyclist was originally traveling. Consider this. If we take maybe half a meter per second, so d of 0.5, and then we take d of 0.6, and we figure out what these numbers are. And then let's see, I'm going to go to the calculator. And back to the calculator, I'm going to clear this. And we have 0.383. And then parenthesis, I'm going to do the 0.5 first. And then we're squaring that. And we get that number, 0.9575. And then we'll do the same thing, except this time it's going to be a 6 here, and then enter. And we get that value. So what we're doing is we're going to take 0.13788 and subtract 0.09575, and we get 0.04213. Let's go back to here. And let's see. So what we did was, let me just quickly write this. Whoops. We took d of, whoops. Let me slow down a little bit. 0.6 minus d of 0.5. And I'm going to round this so we get a number that's pretty close to 0.042. And remember, we're in newtons. Now let's do this again. If we, let's put a line here and we'll work under this here. If we take, say, d of 8 and then 8.1 seconds. If we figure out these numbers and subtract them, we are going to do the same thing, subtract them, and we get a number that's about 0.617. Okay. So here we have the inputs. Notice that we put these values in. They're just 1/10 apart, and they're 1/10 apart here. But the outputs, up here and up here are definitely different. So it varies depending on the original speed of the cyclist. Let's move on. I'm going to slide this up here. Let's consider another power function associated with the motion of the cyclist. And this is the amount of mechanical power. It's noted as m sub p of v that the cyclist needs to generate to compensate for the drag force is expressed by this equation right here. It's the same equation, except that we are cubing. We're raising the v to the third power. So part 4, based on the range of reasonable values for the speed of a cyclist in meters per second, fill in the following table and graph the mechanical power function m sub p on the axes provided. Again, be sure to label the tick marks on the axes, round to the nearest tenth. Okay, so let's think how we can do this. We can use the same numbers. Just gonna, well, let me do this. I am going to copy this down and then slide the screen up. There we go. Now, I'm going to do the same thing. We'll go 0, 2, 4, 6, 8, and 10. And again, m sub p, we'll substitute a 2 in first. We get 0.383, and that would be 2, and this time cubed. 0.383. 2 cubed is 8. And I'm going to go to my calculator and plug this in. I'm going to clear that out. We get 0.383 times, I'm going to write 2 cubed in here, raised to the third power. And I get about 3.064. Whoops, over here. 3.064, and again we want to round to the 10th place, and that would make this about 3.1. If we do the same thing, I'll just do this one more time. How about for the 4? We're going to take 0.383, and we're going to take 4 and cube 4. Back to the calculator, and I'm just going to hit second entry, and then go back and make the 2 a 4. And I get about 24.512. And rounding, 24.5. Now I work these out ahead of time. The same thing for m sub p of 6. This is going to give us about 82.7 after rounding. So here's 82.7. M sub p of 8 is going to be about 196.1. And then m sub p of 10 is going to be 383. And we didn't need a calculator for that. All right, so let's go ahead and start plotting these points. If we start at 0 on the horizontal axis and I plot my velocity, we're going to go from 0 up to 10. So there's my 10. And let's see, we'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, and we already wrote 10. And the top number is 383 on the vertical axis. So why don't we just make that a 400? We'll start at 0 and we'll go up by, instead of 5, why don't we do 50 this time? And then 100, 150, 200, 250, 300, and 350. Plotting these same points, or these points from the table. 0, 0, we plotted first, that's pretty easy. 2, 3, 1, so when I look here on the horizontal axis, I find 2. That's that 2 that I just circled. And then I go up 3.1, which is pretty small of a scale, so it's just going to be barely above the horizontal axis. If I go to 4, we're going to go up to 24.5. Not moving up too much so far. 6, 82.7. Okay, 8, 196. Whoops, I moved the screen up. I didn't mean to. 8, 196. And then 10, 383. Again, we're going to connect these with a smooth curve. There we go. Let's look at number 5. If a cyclist increases his or her speed by 0.1 meters per second, how much does the mechanical power change? Again, it's going to depend on how fast the cyclist was originally traveling. If we start relatively slowly, say 0.5 meters per second, 0.5 meters per second, and we increase to 0.6 meters per second, it's going to be the same basic thing that we did last time. We're going to take d of 0.6, subtract d of 0.5, and when we do that, we're going to get about 0.035. And that's going to be in watts. So I put my W for the units there. And then if we go from 8.0 to 8.1, just a faster speed to start, and we subtract d of 8.1 minus d of 8.0, this time we get about 7.446. Again, we're in watts. So you can see how, again, the inputs were only differing by 1/10 of a point there, but the outputs here are definitely much different than 1/10. Part number 6, moving away from the context of the cyclist, consider the functions defined by f of x equals x squared and g of x equals x cubed. Part A, I'm going to slide this up here. Are there any values of x that would make g of x greater than f of x? And the answer is yes, there are. So let's start by just putting yes here. And then we know if we cube, we'll put cubing a positive number, there we go, greater than 1, will be larger than squaring that same number. If I wanted to write this mathematically, I would write this, we could say something like g of x will be strictly greater than f of x if x is greater than 1. There we go. Part B, are there any values of x that would make f of x strictly greater than g of x? Again, here the answer is yes. And we could start by saying, let's do this. We'll do squaring a negative number will be positive, while cubing a negative number, there we go, negative number will be negative. Okay, if we wanted to write it mathematically, we could say that as f of x greater than g of x if x is negative. There's another case also if x is between 0 and 1. So we could write also f of x will be strictly greater than g of x if x is greater than 0 and less than 1. Part C, using a calculator or app, graph f and g on the same set of axes to check your previous answers. So this is going to be nice. Let me go back to the calculator and bring up the graph. So I'm just going to hit the y equals button. And then I already graphed these in here, or entered the information. And we have x squared in y1's row, and we have y2, the second row, x cubed. So if I graph these, you can see I have two curves graphed here. And just take this in a little bit here, but I'm going to draw these for us so we can differentiate which graph is which. But let me just stop doing that. I'm going to go back to the drawing here and slide the screen up. Now, the f of x is equal to x squared. It's defined to be x squared. It's a quadratic. And I'm just going to roughly sketch this in. Goes right through the origin, then comes up again like that. So there's the graph of f. Now, g of x, or the g function, is the cubic. It's x cubed. So what's going to happen here is it's going to start down here on the left. It's going to come through the origin and then come up like this. So this would be the g function. And this confirms our answers from part A, B, and C, because we can see that wherever the f function is, let me just try a different color here, wherever the f function is above the g function, then that would be greater. So f is greater than g in the interval between 0 and 1, and f is greater than g, from 0 down to negative infinity. So that's a nice way to picture it, to draw the graph and confirm what we wrote out mathematically. Part D, let's just scroll this up here. The positive value of x that makes f of x equal to 2 is called the square root of 2, and it's written as the radical symbol with the 2 under it. The graph of x that makes g of x 2 is called the cube root. Cube root of 2, which is written as the cube root of 2. Some calculators have a cube root button, but sometimes you must enter them as 2 to the 1/3. That is 2 raised to the 1/3 power. Calculate the square root of 2. So let's go and write this. The square root of 2 is approximately equal to, and then we'll do this again. The cube root of 2 is approximately equal to, and we're being asked to round to 3 decimal places. Let me go back to the calculator, and I'm going to raise, let's see, we can do the square root of 2 as 2 raised to the 1/2 power. That's about 1.414 and so forth. And how many decimal places? It was 3 decimal places. So it's 1.414. 1.414. And let's see the cube root of 2. I'm just going to do the same thing, except we're going to raise 2 this time to the 1/3 power. And this is about 1.2599. So rounding, that would give us 0.260. So let's write that down. It's about 1.260, and that 1 looks a little bit messed up. So let me just rewrite a better 1 there. Okay, that's the end of this video. Thanks and take care.